Right. So when we finished class on, what was it, Monday, we finished talking about a simplified version of the Navier-Stokes equation. And that was called the Euler equation. We said, what if viscosity is 0 or really close to 0? How do flows work? That gave us the Bernoulli equation and gave us some information about how flow works, how fluids move when there's no viscosity. What we're going to do now, we're going to jump ahead from chapter 6. We're going to jump over chapter 7. We'll come back to it later. We're going to go to chapter 8. And we're going to look at internal incompressible viscous flow. Okay, so what does that all mean? So internal flow, that means like inside of something, like inside of a pipe or a duct or a nozzle or between two plates, or it's something. It's not like, you know, air blowing over the surface of a car. It's inside of something, so it's flowing inside of something, internal flow. Incompressible, that means density is a constant, incompressible, so constant density. And viscous flow, that means that now viscosity starts to matter. So when we talk about viscous flow, we're going to have now the viscosity of the fluid starts to actually matter. And what that means is we're going to get things like friction actually happening. We're going to get conversion of mechanical energy, like potential energy, kinetic energy, pressure. We can convert that into things like heat because of viscosity. So we'll look a little bit at how that works fairly shortly. But it also means that we can't, if we look at the Navier-Stokes equation, before we crossed out like all of these terms with mu, because mu was 0, and that made things easy for us. If mu is not 0, if viscosity is not 0, then that has to stay around. So we get back to the full Navier-Stokes equations. So there are some things that we can learn, certainly, like we did in Bernoulli's equations. There's things that we can learn from inviscid or viscosity equals 0 type system. But if we really want to understand flow, fluids have a viscosity. So we have to actually consider the effects of viscosity. So that's what we're going to do. We're going to build that kind of back into our thinking, into our models of fluid flow. We're going to do that by solving all 3 of these equations simultaneously for a couple simple cases, just to try to make the connection between solutions to the Navier-Stokes equations and how things are actually working and behaving in reality. And also get some understanding of kind of the power of these equations in describing fluid flow in reality. So that's what we're going to try to do. We're going to do that first for a relatively simple example. An example that we've seen before that we already know the answer to, but we'll prove that that actually is the answer. So let's look at a diagram. You come down here. Let's imagine we have something like this, where we have 2 plates. Okay. They are spaced apart by some dimension. So we'll call this space, or this gap between the 2 plates, D. We'll put some axes on here. So say the kind of across the channel dimension, that's the Y dimension. And left to right is the X dimension. Okay, so this is the flow we're going to be considering. And we're going to be looking at the case where this top plate is moving with some velocity. So this has a velocity in the X direction of capital U. Okay, so how can the Navier-Stokes equation, right? We already know what the answer is. It's nice linear. Okay, great. But how can we get that from the Navier-Stokes equations? So we get that. We figure that out by solving all three of these equations simultaneously. Okay, we have to solve them. But the nice thing is, just from kind of thinking about the system, we can start crossing out a lot of the terms that we see there. So we have to solve all three of those equations, but a lot of the terms in those equations are zero. So we have to figure out, the first step is to figure out what's zero and what's not zero. And then we solve. So our first step is to simplify, then we solve. And we're going to try to cross out as many things as we can. So we'll start with a list of assumptions. So if we think about this particular system, it's reasonable to think that flow is only going to be really left to right. Right? There's nothing pushing the fluid in the y direction across the channel. There's no push that would make it go that way. And there's nothing pushing it like up and down in the z direction. It's going to be left to right. Right? That's reasonable. So if we look at, so flow is only in x direction. Right? What that would mean, that means our velocity vector is equal to u I hat plus 0 j hat plus 0 k hat. So the velocity is going to be pointing in the x direction, and the x direction only. Okay. Again, thinking about this, second thing that we're going to think about, we're only going to consider the case where things are not changing with time. So we're going to look at steady flow. So that would mean that the change in velocity in any of the components with time equals 0. So we can imagine things that are changing with time, say like that top plate is speeding up or slowing down. We're just not going to think about those right now. We're going to assume things are not changing with time. The top plate is moving with a constant velocity. Nothing's changing with time. Okay, next assumption. Well, let's consider the case that gravity is not in the x direction. Okay, maybe it's in the z direction, maybe it's in the y direction, I don't know, but it's not in x. So there's no gravity in the x direction. G of x is a 0. Maybe it's in z, I don't know. Not super important, but let's consider it in, maybe that's in the z direction. Okay, then the last thing, and this will be a critical one. So I think those are all, we can all get on board with, okay, that makes sense for this given problem. The last thing is maybe harder to just come up with. But if we think about how things are going to be changing, in what direction do we expect to see changes in velocity? Like as we go left to right, do we expect to see significant changes in the velocity? Like if we looked at this location versus that location, a location at the middle at one spot and like further to the right also at the middle, would those be a different velocity or the same? We'd expect them to be the same. Okay, the change is going to be happening in y, right? That's where we would expect by looking at this, because the bottom plate is stopped and the top plate is moving. So that's where like things are changing. They're changing in the y direction as we go across the channel. Like the bottom plate right there is stopped, and it's also stopped over there on that other side, and it's also going to be stopped velocities. So in x, nothing about our system is changing. But it is in y as we go, like the bottom plate is stopped, the top plate is moving. Okay, so delete my little scratch marks. So this is the flow is only changing, so changing in y. So it's pointing in x, but it's changing in y. All right, so let's start crossing stuff off. What do these assumptions have to do with our equations? What terms are zero because of these? So we're going to be crossing off a lot of things. So I'll zoom in on the equation so that you can see a little bit what I'm crossing off and why. I'm going to cross it off. Well, we'll just start with the first one. So the flow is only in the x direction. That means little v is 0 and little w is 0. So the derivative of v is 0, like the derivative of 0 is 0. The second derivative of 0 is also still 0. So anywhere I see a v, anywhere I see a w, I can cross those terms off because those are going to be 0, because the flow is only pointing in x. So u is a thing, but v and w are not. So let's start crossing off all of those terms. So this first term, that gets canceled because little v is 0. So what I'm going to do is write, that doesn't mean it goes to 1. That means it's crossed off because of assumption 1. So it goes to 0 because of assumption 1. Okay, this next one also goes to 0 because of assumption 1. What else? So everything else on that top one stays around. So I see no more v's or w's. Let's go to the second equation. Okay, so there's a v. There's a v. I messed up. 1. There's a v. There's a v and a w, so that's extra 0. There's a v. There's a v. There's a v. I'll add my ones in a little bit later. Let's go down to the bottom one. There's a w, 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 w. So those all die because of this first thing that we observed. Okay. Which is nice because we basically killed off 2 whole equations with like one fell swoop. We didn't totally kill off those 2 equations, but we're pretty close. So now both of those equations, the second and the third one, both say that pressure changes because of gravity. That's all that those equations say, which is stuff that we already knew. Like we knew that from our fluid static stuff. So how does pressure change as you go down in a fluid? Rho gh. That's all that those 2 equations say now. So they're okay, that's good, but it doesn't really have any bearing on our flow. So it's still true. Say gravity's in the z direction. So how does pressure change in the z direction? Well, it goes up, rho gh. Cool. So we've solved that equation. Really both 2 and 3. Let's start crossing off more terms. Steady flow. So nothing is changing with time. So that kills off this guy. Okay, that also would kill off that like dv dt and dw dt, but those already were killed off before because we knew those were 0 and they're not changing with time, so they're 0, not changing with time, so they stay 0. Okay, what else? G of x is 0. Maybe it's in z. So okay, so if this is 0, that's 0 there. Then our last is that the flow is only changing in y. So the only changes that we should expect to have in anything are in y. So this is Okay. That is 0 because it's not changing in x. So that second derivative in x is 0. And this is 0 because it's not changing in z. And d pressure dx. Pressure is not changing in x either. We have the same pressure on the left-hand side as the right-hand side. So, okay, so let's solve these three simultaneously. So we'll solve the second and third equations because they're super easy. So what the second equation now says is that the change in pressure in y is equal to 0. dp dy equals 0. Okay, cool. So pressure is not changing in y. The third equation says dp dz equals rho g. So that says pressure in the z direction is rho gh. Okay, that's cool. We solved those two equations. Now we have to solve the third equation, which is the x dimension. So we'll write our simplified Navier-Stokes equation. Our simplified Navier-Stokes equation is d squared u dy squared. Okay. So we went from this big, ugly system of three equations. We're down to a single equation that's relatively more simple. Something that's actually tractable that we can actually solve. We need, to solve this equation, we need two boundary conditions because it's second order. So if we look at our system, what are our two boundary conditions? Boundary conditions are always at the boundaries of the flow. So what do we know about fluid flow at the two boundaries? How do you know that? So because of the, you said it at the end. No slip at the boundary. Because of the no, so we know, what do we know about the flow at the boundary? We know that the no slip condition works. So the no slip boundary condition is our boundary condition. So our boundary condition, the no slip boundary conditions. So that gives us two boundary conditions, one at the bottom surface, say that's at 0. The velocity is 0 because that bottom surface is stationary. At the top surface, the velocity at d, at that top surface, right across the channel. So the velocity here at the bottom is 0 because that wall is 0. The velocity here at the top at d is capital U. All right, now all we have to do is solve this relatively simple equation, right? This is the equation that you pray for on a calc exam. Like, please solve a second order differential is equal to 0. So let's, if you flip it over, let's actually go and solve that and see what our equation says. So we have, our equation is 0 equals mu d squared u dy squared. Just a note on this for notation. If we look back up at these, if you look at this, that's like the little like partial derivative kind of leaning over d. If you look at what I just wrote, it is now a normal standing up, normal d. The reason for that is because we went from initially the Navier-Stokes equation describes things that can change in multiple dimensions, right? U could be changing in x, it could be changing in y or t or z. But now we've kind of pared it down where we know it's only changing in y. So we went from partial derivatives to normal derivatives. Do you have a question?
Yeah, the last side of that first equation, did you get across the x?
Yeah, I did that last time too. So I meant to cross out, okay, so for number 4, flow is only changing in the y. So that means this guy gets crossed out too. Because U is not changing in X, it's changing in Y. Yeah, thank you, good catch. All right, I did the exact same. You like get crossing out too many things and then you forget them. But yes, that was supposed to be crossed out. Okay. So this is our differential equation. We just have to solve this by integrating twice. First, we can divide off by viscosity because we have a 0. So 0 equals d squared u dy squared. We integrate one time, and right, we can say that du dy equals 0 dy. And then we integrate. So du dy equals c1. Just some unknown constant. And then we can separate variables and integrate again. Du equals c1 dy. Now we integrate both sides. We get that the velocity u is equal to, this is c1 y plus an unknown constant, c2. Okay, right? If the second order differential, if the second derivative is a 0, then that means that the original function was linear. Okay, we have two unknown constants. To find these unknown constants, we use our boundary conditions. So we'll use boundary condition 1, told us that u of 0 is equal to 0. So this tells us that 0 equals c1 times 0 plus c2. Right, plug in the boundary conditions. So C2 must be 0. And then our second boundary condition here was that the velocity at D is equal to capital U. So we plug those in. So capital U equals C1 times D. So we get a value for C1. C1 equals capital U over D. And we put this all together. Our velocity vector is equal to capital U over D times Y I hat plus 0 J hat plus 0 K hat. So this is our velocity vector. If we look at what that is a line with slope U over D. So it goes from 0 at the bottom plate to capital U at the top plate, and it's changing linear between those 2 points. So if we look at that, which is great because that's what I told you before, so I wasn't lying, or at least not trying to. That's going to look something like this, right? So a flow between two parallel plates, this is what we've drawn before when we figured out like Splash Mountain and what the viscosity was and what the shear stress, like we've drawn this before. Lo and behold, that came from a simple solution of the Navier-Stokes equations. So that's cool, but does it actually happen in real life? So that's what we'll look at now. We have a little bit of a demo. It should be kind of fun. We're going to look at a system where we have sort of this going on. It's not going to be exactly this because two parallel plates that extend at infinity in every direction is kind of big, so I couldn't fit that in the classroom. But we have like the next best thing. So I'm going to give me a second to change over to my phone. So our virtual people can see. Okay, can you guys see me on my phone now?
Yes, we can.
I think so.
Yeah, we can.
So we'll turn it around, say hi to everybody. Okay, cool. So what we're gonna do is I'm gonna give this to Josh. So you can be our videographer. I'll make this big so that you guys can all see how bad it is.
Thanks.
I have too many, I have like 4 things on. No, that's not the right one. Come on. Pin the other one. Okay. Cancel. No. Something will get it. All right. Cool. So you can see now on the TV. All right. So what we have here is a system that's kind of like the one that we just talked about. Okay. Instead of 2 parallel plates, we have 2 cylinders, one inside of the other. So we have a cylinder that I can turn on the inside, and then a stationary cylinder on the outside. So this is our stationary plate and our movable plate. What we should see, right, is a nice and linear velocity between those two. Okay, it's going to curve because they're cylinders, but it should be linear between the two, where the inside surface is going to move at the speed that I'm turning the cylinder. The outside surface is going to be stopped, and we should vary linearly between those two. So we're going to look at that by putting some dye into our fluid. The fluid that we have here is corn syrup. It's light corn syrup, apparently with real vanilla. So it's horrible and sticky, but the nice thing about this is the viscosity is fairly high. So what we want to have is we want a situation where, okay, I'm not going to be perfect and have no time component to this. So we said in the solution that we just did, like du dt was equal to 0. I'm not going to be able to make that happen because I'm going to be shaky and it's not going to be perfect. But if we use something with a high viscosity, then viscosity wins and that term's bigger than the du dt term. So this also works with lower viscosity things, but then you have to be better at having the thing actually have steady flow. So we use corn syrup. We bought out, I think it's like 7 bottles of corn syrup in here. So very sugary. So what we have, I have some food coloring that I put into syringes with very scary needles. And what we're going to do is inject the dye into our fluid so that we can visualize what's happening. What we should see is relatively slow velocity as we get out to the edge, and faster velocity as we get up to the front of it. So we'll inject. I'll just make like a couple blobs. Oh no. Okay. It was very exciting. Okay, so I have a red blob and a green blob, and I'll put a yellow one kind of in between. Okay. So can you see, you can kind of see those on the screen. All right, so we have a red blob, a green blob, and a yellow blob. Did I do them in traffic light order? I did. So green's supposed to be in like traffic light. Green, yellow, red. So as I turn the handle, we should see the green one move the fastest. The red one is pretty close to the wall, so that should kind of hardly move. So let's see if that actually is the case. Pretty cool. So they move, the green one moves the fastest because it's closest to the moving surface. The red one basically is stationary. If we continue to crank, see how well I can do this. If we continue to crank, that should keep going. And our green dot should keep moving fastest. Our red and yellow dot should be fairly slow. So our green dot has made it around. The red dot is still basically at the starting line. Okay, so that's like 1.5 times around. Okay, so that's 1.5 times around. So we're coming up on 2 times around. So our yellow one just made it around once. Our red dot is like back by me. It's very exciting, isn't it? Really. Okay, so the red dot is just starting to come around. The green dot has made it around, I think, 3 times now. And the red dot is like just barely, it's kind of smeared out, but it's just barely making its way around. So what happens, and for those of you virtually, it's kind of hard to see this, but what happens if we crank the other way?
Everything goes back. It's original.
Does it go back perfectly?
No.
Yes, it should, right? Because you don't have time in it.
Yeah, so there's no time component. So if we reverse the boundary conditions, we should be able to, again, if I didn't shake it very much, we should be able to get back to the same spot, right?
In theory.
Okay, let's see in practice. So if we go backwards now, I think I did like 5 cranks. So that's 1. It's 2. That's 3. See them mixing? Turn around, how's the red dot doing? It's coming.
That's pretty
Here they come.
That's crazy.
Isn't that wild? So they get smeared up a little bit because I am shaking it a little bit, and the starting and stopping has to be basically perfect for them to not mix at all. But you can tell, I mean, they pretty much come right back to the same spot. When you look at it, once I mix it up, if you look at it from the top, it's really cool. I'll do that in a second. But it's pretty cool. You see, like, basically they look like concentric rings. So the little dots get smeared out because, like, the front half of the dot is moving slower than the back half of the dot that's closer to my center pipe. So they get smeared out like perfectly. You get these really thin, like, dye stripes in the fluid. It's pretty fun. The other demo that I want to do, this one's a little bit harder to see, but maybe with the video camera you can see it. We're not going to do the solution for this, but another thing that we've said happens, and we haven't actually shown it, is when you have a jet of fluid moving at uniform velocity and it crashes into something hard. What we've said happens is the fluid, we've kind of described the velocity, it goes like this. You plotted those streamlines. So what we should see happen is if there's a hard surface, we should see basically the fluid's going to slow down as it gets closer to the surface, and when it does that, because of conservation of mass, the area has to increase. So what we should see in this is, I'm going to pour corn syrup. It's going to be very exciting. We're going to pour corn syrup, and it should be a thin stream, but as we get closer to the surface, we should see above the surface of the corn, like above where it crashes, we should see it start to expand and kind of become a cone shape before it goes to the left and right. So again, you might need to come really close to this, but if I just pour it, I don't know, it's hard to see. You guys can come and do this for yourself, or next time you're pouring honey on something, it's very exciting to try. Because you can see it actually extends just with the corn syrup, that you can see the velocity change extend like a couple centimeters up off of the surface when you have water. You can also do it the next time you see a faucet when you're washing your hands. Take your hand and raise it up closer and closer to the faucet, and you can see above your hand that the water coming down and hitting your hand will expand out quite a bit as it comes and hits your hand, and you see that velocity change. And you can kind of see directly the relation of like the area of the jet versus the speed of the jet as it's coming in and crashing into your hand. So we'll leave this up here. As you guys are coming out, you can take my camera back. As you guys are walking out of the room, I'll leave this here, and you can come and try to break things. I have to figure out how to stop video on this. Okay. How do I do this? Okay, I think I have to. Okay. All right, so you guys can see that again. Virtual people can use, hopefully you can see my screen again. Okay, so hopefully you see our notes again. Okay, can somebody tell me in the chat? Okay, looks good. Thanks, David. Okay, so I'll leave this. As I said, we'll try to end a few minutes early, and hopefully you can come by and turn the handle and watch what happens. It's pretty fun. Okay, the next problem, we won't get done with this, but the next system that we're going to do is look at a different system just to kind of get a sense of how we can cancel out things for different types of systems. So the next system we'll look at is, again, a two-dimensional channel. So generally, we're going to stick with relatively simple geometries and simple flows, because that means simple differential equations. In this flow, okay, same basic thing. We have a distance across the channel, d. And in this flow, we have both top plate and bottom plates stopped. So this, like capital U equals 0, capital U equals 0. So both of those are stopped. But what's driving our flow in this case is high pressure on the left side and low pressure on the right side. So this would be something where we have two parallel plates and we are pushing with pressure, we're pushing fluid through those plates. So let's see what happens to our equations with this. So we're going to have a lot of the same basic assumptions. So if we kind of remind ourselves, so flow only in the x direction, steady flow, G is 0, flow is only changing in Y. So we're going to have a lot of the same equation or the same assumption. So flow is only in X. Direction. So that's right. Little v equals 0 and little w equals 0. That's going to be the same for this problem too. There's nothing kind of pushing the flow. If you can imagine, we're going to have the flow from left to right, not up and down or across the channel. So if that's true, then any little v or little w can be crossed out. So that will let us cross out this one, this one. From the top equation, it will let us cross out the entire second equation, really. And the entire third equation, just like it did before. Okay, so all of these get killed because of this first one. Right. Okay, second, steady flow. Right, which is that the velocity is not changing with time. That allows us to cross out this first term, du dt. Okay. Gravity is equal to 0 in the x direction. So no gravity in x. So we can cross out this term. Gravity, maybe gravity is in z again. Gravity is not in x. And then our last thing, so pressure. Pressure changes in x. Velocity only changes in y. So again, if we look at our system, we kind of, by definition, the pressure is high on one side on the left, the pressure is low on the right. But we expect the velocity to only change in y. Like the bottom plate, it's going to be stopped, it's going to be fastest in the middle, and it's going to be stopped again at the top. So it's going to be changing as we go across the channel, but it's always going to be the fastest in the middle, like as we move left and right. And it's always going to be stopped at the walls, whether we're left or right. That's not going to change. So what's only going to change is the velocity in the y direction, but pressure in the x. So dp dx, we can't cross that out because pressure changes. But we can cross this out. We can cross this one on the second term on the far left. Because du dx is 0, and we can cross out d squared u dz squared because of that. So what we would be left with for our system, for our simplified Navier-Stokes equation, we would have 0 equals minus dp dx plus mu, not a partial, d squared u dy squared. And we would have two boundary conditions, which would again be the no slip boundary conditions. So at the bottom plate, our velocity is 0. And at the top plate at D, our velocity is also 0. So in order to figure out what's happening in this flow, we then have to solve this differential equation. that should hopefully be able to describe fully what the flow looks like. So we'll do that next class on Friday. For now, we'll wrap up. If you guys, as you're walking out, feel free to give the little fluid thing a spin, and yeah, have fun with that. Have a good Wednesday, and we'll see you back on Friday.